structure is broken down into tracks, sectors, and clusters. So disks are spliced up into these circular rings known as tracks. Tracks are made up of sectors, and this sector size is actually determined when the disk is created by the manufacturer. We can't change those. Older disks were broken up into 512 byte sectors. Newer disks, however, use 4 kilobyte sectors. Now, a contiguous section of these sectors is known as a cluster or block. In Windows, that term is known as an allocation unit size, or an AUS. And this is the smallest amount of space that Windows can allocate on disk for a file. Now, this is important because we can configure this value via the allocation unit size when we format a disk. And we're going to want to do that based on the size and type of data that is hitting our volumes. It really comes down to a balancing act between storage space, wasted storage space, and performance. For example, let's say that we bought a 16 terabyte disk from a manufacturer. When that manufacturer created this disk, they set up 4 kilobyte sector sizes. Now, we create a volume and we format it with, say, a 16 kilobyte sector size. Now, let's say that this volume is built for users and they're storing a lot of small files onto this disk. Again, what's the smallest amount of space that Windows is going to allocate when a user creates a file? Right, it's going to be 16K, right? So let's say the user is creating a bunch of 1 kilobyte files. Youch! It's going to take up that little bit of space, and this is all wasted space, otherwise known as slack space. And you can actually see that slack space in Windows whenever you look at the properties of a file. You'll see size and size on disk. So the size is the actual size of the file. The size on disk is the size of the cluster, or clusters if that file required more than one. Now, 15K isn't a lot of wasted space for one file, but imagine a lot of users with a lot of small files, and that could add up quickly. We can get much more efficient use of our storage space by turning our allocation unit down on a workload like this to, say, 4 kilobytes, which would be the lowest we could go since that's the sector size here for this disk. Now let's talk about the other side of this, performance. Let's say that instead of storing small files, we were storing big files, and our average file size is around 1 gigabyte. That's going to result in a lot of clusters, right? One file is going to take up hundreds of allocation units. And here's why this is a big deal. Because disks read and seek an allocation unit at a time. So that means more clusters is going to result in more work for the disk, which is going to result in lower performance. If we were to take this 16K allocation unit, maybe turn it up to 64K, we would get far fewer clusters, which would result in better performance. So the bottom line is this: understand the kind of workloads you need to support, and then create a volume that targets each individual workload. And then tweak that allocation unit based on the average file size going on that volume. Imagine if you just had one big volume and you stored everything, right? IT stored their ISOs and their backups in there. We stored our VHDs on there and user data. That would be one highly inefficient drive because of the mixed workloads going onto that volume. We'll look at how to do that in the virtual lab here shortly. Now, another decision we're going to need to make is what partition style we're going to use to configure our disks with. As soon as we bring a disk online and initialize it, we're going to need to choose between MBR, master boot record, and GPT, the GUID partition table. Now, MBR has been around for a very long time. So because of that, it's highly compatible with older systems, which is really about the only time we'll be using this partition style. There's one other use case too we'll talk about here shortly. But because of its age, you can start to see its many limitations. In fact, its partition table is only stored in one spot. And by the way, disks need a partition table so they can keep track of all the partitions that we end up creating on the disk. But this partition table is stored in the boot sector on our disks. And the downside is that it's only stored in one place. So if that sector ever becomes corrupt, well, you're done, and Windows won't be able to boot. On the other side, the GUID partition table is stored with every partition table. So we have that redundancy, and it can fix itself if corruption were to ever occur. We also have a limit to the number of partitions with MBR. 4 is your max. You can get around this by creating 3 primary partitions and then 1 extended partition. But look at GPT, 128 primary partitions. Same with the volume size, up to 2 terabytes here with MBR, up to 18 exabytes with GPT. Now, one of the primary reasons we still see MBR around on the server side today is because there's no limitations around booting. We can create MBR boot disks that run on old BIOS-based firmware. GPT requires UEFI firmware in order to boot from. So the bottom line here is use GPT whenever possible, always for your data disks and where you can for your boot disks. About the only reason you use MBR today is if you have older systems on BIOS-based firmware and you need them for your boot disks. Finally, we need to determine what file system we're going to format our volumes with. REFS, the resilient file system, came out back in Server 2012. And it's really grown up here in Server 2016. Microsoft touts this as the file system of the future, and someday it's going to completely overtake NTFS. And that's because it's a far more efficient, and as the name implies, resilient file system. One of the big draws to REFS is the fact that it has self-healing powers. In fact, it has built-in checksums that can automatically detect errors and corruption. And then, when it does detect them, fix them as an online operation. So we never have to run our own check disk. We never have to take volumes offline. All of that is handled under the hood by REFS. It's also highly optimized for our Hyper-V workloads. In fact, almost all of your virtual hard disk operations are instantaneous. Things like creating a fixed size VHD, merging VHDs, resizing VHDs, and even taking production checkpoints, instantaneous. Under NTFS, those took hours to do because NTFS needs to work down there at the block level, at the disk level. So if you were to create a fixed size VHD, it would literally need to go and zero out all those blocks on disk before it was ready. That's why it took so long. Not with REFS, because everything is a metadata operation. It actually creates a very highly efficient database-like structure known as a B-tree, and it uses this metadata to keep track of everything on disk. So that's why everything is nearly instantaneous. So it's a perfect fit for Hyper-V. It's also a perfect fit for our file servers that store large amounts of data, especially things like backups. Backups inherently contain a lot of the same data, and REFS has a feature known as block cloning. So whenever we take a backup, if those bits are already on disk, it can simply clone them, which can dramatically decrease the amount of time it takes to perform a backup. So all of those reasons and more is why REFS is now the preferred file system in Server 2016. But the only time you wouldn't use REFS is if you can't. There are some limitations. So it does not support some NTFS features like file system compression, file level encryption, although you can still use BitLocker for volume level encryption, data deduplication, disk quotas. It's not supported on removable media, and no, you cannot boot from an REFS formatted volume. You will need NTFS for that. All right, I think we're ready for the virtual lab. We're going to take all that we learned about here and put it into practice by configuring multiple disks that target specific workloads on a file server. So here we are on our file server, fsnug, and let's start by initializing and configuring a single disk in the graphical user interface, and then we'll use PowerShell for the rest. So let's right-click on the Start button and get right in to disk management. We'll go ahead and give this a maximize, give it a second to load up our configuration, and you'll see it's going to prompt us right away to initialize any uninitialized disks. Again, we have 3 of them here. By default, it's going to choose MBR. We're going to choose GPT, and let's just choose disk 1. I'll show you how we can initialize the other 2 again using PowerShell. So we'll initialize that first disk here, and while it's going on here, let's get some room to work with. All right, there we go. So our disk 1 here is now online, and it is formatted with the GPT partition style. By the way, disk 0 we configured way back when we installed Server 2016. That is our boot disk. There's a system partition and the primary partition where Windows is installed. And if you want to see the partition style, you can just right-click, head into Properties, and go over to Volumes. See, we've got Master Boot Record here as our partition style. And if we choose the disk that we just brought online and initialized, we should see this is GPT. There it is, GUID partition table. Cool. So this first disk, we're going to target user data. So let's stick with NTFS for this, and we're going to choose an allocation unit size that's fairly small because we expect a lot of small files from our users. So you can right-click either on the disk or on the unallocated space here, and let's choose New Simple Volume. We'll walk through a real simple wizard here, specify how much data we want to use for this volume. We'll just use all of it and hit Next. Let's assign this the drive letter of U, so we know that this is user data. Choose Next. And now is where we choose our file system, our allocation unit size, and we can give it a label. I'm going to call this user data. Now let's choose our allocation unit size here. And by the way, default here is going to change depending on the size of your disk. It actually scales up. So for a 16 terabyte and under disk, the default allocation unit size is actually 4K. So we could choose this or stick with the default for our disk since it's under 16 terabytes. Once it hits 32 terabytes, it scales up to 8192, 64 terabytes, and it just keeps on going up. So this is why you may want to mess with the default, because if you have a huge disk, but you're going to store user data on it, the default could be 32 or 64K depending on the size of that disk, and you may want to scale that back a little bit. So let's set up here 4K for our NTFS formatted user data volume. Hit Next, hit Finish, and it's done. And there it is, an NTFS formatted U volume with a 4K allocation unit size. Now, why did we choose NTFS for this kind of workload? Yeah, because we're going to want some of those NTFS features, right, that REFS doesn't support, like disk quotas. We're certainly going to want to enforce disk quotas on our users and give them the ability to perform file level encryption, just to name a few. Now, the next two disks here, we're going to configure one for the IT department, right? We're going to have a different workload. We're going to want to store our applications and our ISOs and our scripts and all that stuff. And then we're going to have disk 3 here specifically for our virtual machines, for our Hyper-V workloads. And let's do all this in PowerShell here. So I'm going to minimize disk management. Let's head right into the file system here, right into Nugget Lab, right-click on ps-commands.ps1, and fire it up in the ISE. All right, the first thing I wanted to show you here is all of these disk-related commandlets live in the storage module. So if you want to get command passed in the module of storage, you get a nice list of all the things we can do here at the disk level. I'm going to go to split screen here. The first commandlet we're going to look at here is get disk, just a very simple commandlet that you can use to view all of the disks on the system. Here they are, and you can actually see their partition style. There's our boot disk, their MBR, which by the way is an IDE disk, which is why it says virtual HD. These other three are all connected to SCSI controllers, which is why they say MSFT virtual disk. And we formatted that first one using GPT back there in disk management. Now we have 2 raw disks, meaning there is no partition style on them at all. So our next step then is to take disk number 3, which is index number 2, since it's 0 based, and partition it with the GPT style. And we have a very simple commandlet there called Initialize Disk. This is exactly what we did in the UI when that dialog box popped up. So pass in the number, pass in your partition style, GPT or MBR, and run it. And it'll just take a second, and now we're initialized. You can flip back to the GUI here, and you can see that we are now initialized and online. Cool. Next thing we can do is get a list of all the partitions currently on the disk. This will list all the partitions out. There's the partition we just created our U drive on top of. Now let's create a new partition on that disk we just initialized. So we can run the new partition commandlet, pass in again the number of the disk. We're going to use the entire size of the disk and assign it a drive letter of I, because we're going to create an IT disk here to store all of our IT data. Now we can also run a get volume here. This will show us all of our volumes in their current state. There we have I as a drive letter, but you can see we do not have a file system on here yet. And you can actually see that back in disk management as well here. You can see that we have raw, so we have no file system, just a partition at this point. So that's going to be the next step then. We can run a format volume. We choose what drive letter we're going to partition, pass in our file system. Let's use REFS, our allocation unit size. Let's use 4K for this one as well. By the way, for REFS, you only have 2 choices, 4K or 64K. And then we'll specify our file system label here as IT data. So this will just take a second to format that volume. And when we're done, we should have an REFS formatted volume down here as the I drive with a 4K allocation unit size. There it is. You can also see it up here. Now for our final one, we're going to say this is for our VM data. And rather than do this line by line, I'm going to show you that we can do it all in one shot. This is pretty cool. So we're going to run a get disk, and then we're going to filter out all those disks. So we just get that disk that is uninitialized, right? We can just highlight this block of code to run it, and this will just show us that disk, and there it is. So currently there's no partition style on it, no partition, no volume. So that's next. Next up, we're going to initialize it, right? Pass in GPT. We need to run pass-through here. If we didn't do this, the command would end right here and terminate. Pass-through means it's going to take that object that it initialized and pass it, pipe it, as we call that, to the next commandlet, which is going to create a new partition and assign it the drive letter V, use the maximum size, and finally we're going to pass all of that to format volume, which is going to format it as an REFS volume, and we're going to specify our allocation unit size as 64K. Why are we doing that? Because we're storing our VHDs, right, our virtual hard disks on here. So the bigger, the better. This is going to be the perfect volume for storing our Hyper-V workloads. So highlight all of that, hit run, and it's going to do everything we did as one-liners above all in one shot. There it is. Cool. Now if we head back to disk management, there we go. All of our disks are here. And if we head into the file system, don't you love it? Every time you do this, it's always going to pop this up and ask you to format it. Just open those up and hit cancel. But if we head back to the file system here, go into this PC, look at all of those beautiful drives, each one targeting a specific workload. And we're going to be using this as the starting point for the rest of our storage base.